Hi, Conceptual Physics. It's Mr. Fumato here with a how to do household electricity calculations. I sensed in class this morning that a lot of you were a little sort of, uh, not certain on some of the details. So we're going to start with an example of a sticker, an electricity sticker from my refrigerator. So I just want to point out that there's a lot of information on these stickers, but a lot of that information is not particularly relevant for what we are interested in. So let me just explain what I mean by that. So you can see here that there's a lot of stuff that's kind of just not what we're interested in. But we've got three pieces of information about the electrical characteristics of the appliance. And the way to tell the difference, you can certainly look at the names of voltage and amperes, but really the best thing to look at is the label. For voltage, V is for voltage, and A is for amperes. If you see something that says Hz for Hertz, you're familiar with Hertz from back in the fall when we talked about frequency. That's actually the frequency of the alternating current electricity that's coming in. That's 60 Hertz is the standard for frequency in the United States. So basically what we're going to do to start this problem is we're going to write down what we learned just by reading the label. So let me just get rid of those marks and write down that we know that the voltage, V, is 115. I'm going to use 120 because that's sort of what we were talking about today. That the voltage is 120 volts, that's typical socket voltage. And that the maximum current was 3A for amperes. So it's important that you can sort of say, all right, well, the information off of this sticker is starting to remind me of stuff that I've been calculating in my physics class. So how do I know? Well, let's look at the labels, volts and amps. So the first thing I asked you to do in class today was find the resistance. And if you were careful with your reading and you were paying attention in class these past few weeks, you know that there is an equation that relates voltage to resistance. If I want resistance and I know current and voltage, this would point me to this thing called Ohm's law. Ohm's law says V is equal to I times R. Now you'll notice that you have in your wanted column R, so you want to solve this equation for R by dividing both sides by I, and then canceling out the I on the right hand side. I'm also going to rewrite this. I like to put my solved variables on the left. So resistance is voltage divided by current, and I can just plug in the numbers from my sticker, 120 volts divided by 3 amps. That indicates that the resistance inside the refrigerator itself is roughly 40 ohms. Now I'm making some simplifications here, but let's just say that that's a good representation of the resistance inside the refrigerator coils. Okay? So that's one of the first things I asked you to calculate. Another thing that I asked you to calculate was I guess I can go without graph paper. Hey, live a little. The power. So if you remember that there was a formula from the reading that power is current times voltage. If I want power and I know current and voltage, actually now I know resistance, so that's kind of nice. I can just plug again into my equation 3 amps, the numbers from the sticker, times 120 volts, and that gives me about 360 watts. Okay. So again, there's two main equations. There's the power equation, and then from the previous problem on the previous page, there was Ohm's law, V is equal to IR. So then let's just continue on a little bit and talk about the idea of energy consumption and the cost for the consumption of a certain amount of energy. The formula for energy in terms of electrical power is P times T, or power times time. Let's think about that for a second. If power is the rate at which you consume energy, then that rate added up over time gives you the total energy. Remember the analogy I talked about in class today. when you buy a bag of Doritos, they don't care how fast you eat the Doritos. What they care about is how many Doritos you bought, right? Like you could eat the Doritos really slowly or really quickly, and it's still $1.99 or whatever a bag. So you can buy 10 kilowatt hours and go through them really, really fast by putting all the appliances on at once. You can buy 10 kilowatt hours and make them last over a long time by being very judicious about your usage of electricity. The electricity company is charging you for energy, not the rate at which you use it, but how much you use. So the point I'm making is that this is the thing that has a cost associated with it, not power, but energy. So we assumed in class today that the cost was 18 cents per, here it is, the kilowatt hour. That's the unit of energy. Well, why would we use such a strange unit of energy? Because don't we have joules and things like that? Well, because think about this equation. If power is a kilowatt and time is measured in, let's say, hours, then sure enough, a kilowatt hour, not a kilowatt per hour, but a kilowatt hour, is a unit of energy. So let's say that I left my refrigerator on for 1/2 an hour. I have a 360 watt appliance on for 1/2 hour. The total energy consumed is the power times the time. But I just want to point out that because all of the problems are going to involve power measured, the cost of energy in terms of kilowatt hours, we're always going to convert the power into kilowatts. Not watts, but kilowatts. So let me just do that over here in the lower right-hand corner. Kilo means 1,000. A kilowatt is a huge unit. A watt is a smaller unit by a factor of 1,000. So the 360 watt refrigerator, that's a big number to describe something, but if I'm going to make the labels bigger, the number has to get smaller. So it's 0.36 kW, kilowatts. So back to my energy calculation. I've got 0.36 kilowatts times 1/2 an hour. That's 0.18 kilowatt hours. So if if the refrigerator is running for 1/2 an hour, my refrigerator is going to consume almost 0.2 kilowatt hours. So if each kilowatt hour is 18 cents, then the total cost for running my refrigerator would be 0.18 kilowatt hours times 18 cents per kilowatt hour. Oh, wow, I've got an 18 times an 18. Well, I'm not even sure what that is. Let me just bring it up on my computer here. I'll bring up my little calculator. 0.18 times 18 is 3.24 cents. Turns out that it's not that expensive to run my refrigerator for 1/2 an hour. However, the refrigerator is on 24 hours a day, 7 days a week. It's going to cost me about 6 cents an hour. And that's going to add up over time. So I think you can start to see with the refrigerator and then all of the other electricity, it adds up. So each individual kilowatt's only 18 cents, but you use a lot of them. So that's it for now.